I'm live? Okay. Well, welcome to Denver Open Source User Group, February 1st, 2022. Ginormous crowd here tonight. Appreciate everybody coming out. Clap, clap, clap. Okay. Well, our sponsors tonight, obviously, Thrive Workplace. If you haven't checked them out, come here in person sometime, and maybe you can get a tour if you arrive early. We've got Okta Developer sponsoring the video tonight with Matt Rabel. PeerSource, a recruiting firm, has supplied us with the food tonight. They usually do the beers, but we thought we'd switch it up tonight. And we have another, oh, no, they left. Okay, Agile Learner, which is one of Venkat's products, I guess. You get videos, very well done videos, and we are going to be giving away one subscription, maybe two tonight. One for the online people and one for the people here. And the same thing with JetBrains product. No Fluff, Just Stuff is a longtime supporter of us. We get a lot of our speakers from Jay Zimmerman. And I think that's about it. So next month we're going to have Craig Walls, author of all the Spring books, but he's also interested in Alexa, so we might get an Alexa talk next month from Craig Walls right here. So I think that is about it. So tonight we have Dr. Venkat Subramaniam, and he's going to train us on how to move from imperative to functional programming. So take it away, Mr. Venkat.
Thank you so much. Thank you, Dan, for all your efforts to organize. Thanks, everyone, for being here. And for those, oh yes, I need the microphone. Excellent. Thank you. All right. Well, thank you so much, Dan, for all the efforts to organize this. Thanks, everyone, for joining here. And thanks for everyone who are online as well. It's a great pleasure to be here to talk about something that I've taken as a journey. And this comes after a few decades of programming in imperative style. And when I started learning functional style programming, a lot of people were saying, oh, it's really easy. And that even made it worse because it was not. And thinking in functional style actually takes a lot more effort. And I remember one particular experience. I was on a long flight from Europe to back to the US. And as soon as I sat down, I took a piece of code which was easy to write in imperative style. Only took me a few minutes, maybe 10, 15 minutes to write it. And then literally I spent almost the next 8 hours trying to figure out how to write that in functional style. It was so bad, the flight attendant came multiple times to check on me to make sure I was actually okay. And then, of course, at the end of 8 hours, they say hindsight is 20/20, and you're like, duh, why did I not see this? And I was able to make it work in functional style. So I'll share with you some of those learnings. How could we really go from imperative style to functional style? But first of all, just a few different concepts I want to just highlight before we get into the code. We all have been programming in imperative style for a very long time. And imperative style is where we tell what to do, but we also say how to actually do it. So we have to sit there and specify every single step of writing the code. And that's an effort we take to really be very thorough in giving every single step. And in a way, if you really think about it, I would say imperative style is like talking to children. You have to say everything, and you got to repeat that again the next day. A declarative style, on the other hand, is where you focus on what to do and not as much on how to do it. And essentially, in this case, you let underlying library of code to really do the work. Essentially, it's a process of delegation. So you convey what you want to do, and you delegate to other library of code which can get the work done. Now, obviously, the question is, why do we want to really think about and talk about declarative style? And the reason is, it turns out that functional style of programming actually is declarative style of programming. Not all declarative code is functional, but all functional code is declarative. That's one of the reasons why I get excited about functional style of programming is that I'm going to say that functional style is actually equal to declarative style, and you could say plus the use, in this particular case, of higher order functions. So it's really a combination of these two that really what makes a code functional in nature. So every time you write functional style code, you're really expressing the code in this declarative style, and that's where the power of expression really comes in. And of course, you're able to use higher order functions. Well, then the question really is, what in the world are higher order functions? Well, we are used to passing objects to functions, data to functions. We can also pass functions to functions as well, and that's what makes a function a higher order function. So a higher order function is capable of receiving a function as an argument rather than just an object or data as an argument. But of course, one of the things we often hear about when it comes to functional style of programming is we are told that we need to really favor immutability. And that becomes a burden in the beginning because we're not used to it. But immutability is so critical in functional programming, and part of the reason for that is really that functional programming code is optimized, and it is optimized for what's called lazy evaluation. And if we perform impurity or mutability in code, then the lazy evaluation goes haywire, and what's the point in writing elegant code that gives wrong results? So it's really important to honor immutability. In fact, I would say functional programming relies upon lazy evaluation for performance, and lazy evaluation relies upon immutability for correctness, and that's one of the reasons why that's really critical. And the last two things I'll just quickly highlight here is that functional composition and lazy evaluation are really important parts in functional programming. So when it comes to functional programming, we compose using functions, much like how we compose using objects. For example, if I were to take a pen on my hand and say, what is this? Immediately everybody would say that's a pen. But as we know, a pen is made up of several parts, and each of the parts themselves are made up of other parts, and we could even go all the way down to atoms and molecules and electrons and protons. But then we are really good at abstracting and say, oh, that's a pen. In a similar way, we can do functional composition as well, where we can compose functions using other functions, and as a result, we can just build upon an abstraction of functions to build into more complex functions very easily. But of course, one of the really cool things about using functional programming is that the code is extremely expressive. The code is elegant, it's beautiful, it removes accidental complexity, and the code is easy to read and easy to understand. But of course, as we all know as programmers, elegance is not going to go too far. I have this saying, both in programming and in human life, cuteness is not sustainable. For the humans, I would say that's 2 years of living. At the end of 2 years, we say, oh, the baby is cute. Now we say, shut up, you're talking too much. Well, cuteness is not long lasting, unfortunately, in humans, so in code. So if we find that a code is really cute, very soon we're going to ask the question, but what's the performance? Well, make no mistake, there are languages, for example, Ruby and JavaScript, and I'm not saying anything bad about these languages, but an observation, I love these languages for what they are, but at the end of the day, if you write code in Ruby or JavaScript directly, you can get elegant code in terms of functional pipeline, but you don't have lazy evaluation. So not all languages that provide functional style actually provide lazy evaluation. But I'm going to say that object-oriented programming, if you think about it, polymorphism is to object-oriented programming as lazy evaluation is to functional programming. So if you don't have lazy evaluation, then you are got a cute code, an expressive code, but you're not going to have good performance. So it's extremely important for us to be able to bring that lazy evaluation for performance reasons, and we can benefit from that. Well, enough talking, but let's talk about how would we go from really an imperative style to more of a functional style of programming. So I'm going to work with a few different exercises to move us in that direction. So the first thing I want to focus on here is a function that's going to tell us whether a given number is a prime number or not. So let's take a look at an example here to begin with and see how we are able to make use of that particular function in here. So let's start with a little example of a function right there. So oops, let me give this a try again, so give me a second. So I'm going to start with a little example of a function. And in this case, we're going to say that we're going to find out if a number is prime. Let's take a look at the isPrime function for a minute. Now, when you look at the isPrime function, this is quite familiar to a lot of us. We have a Boolean variable divisible set to false. We have a for loop where we say I is 2 to less than a given number. And I think we're getting a feedback here into the room, Matt. So essentially, in this case, we have a variable divisible is set to false. And then we have a loop I equal to 2 to I less than number. And then, of course, in this particular case, we say if number is divisible by any number in that range, we want to set divisible to true and bail out of this loop. And then, of course, return number greater than 1 and is not divisible. A pretty plain vanilla imperative style code. But in the main also, you can see we have a fairly straightforward external iterator that simply loops through and provides the values. Now, before we touch this code, one thing I want to emphasize. The code works, the code runs, but typically one of the things I encourage my programmers oftentimes is if you're taking the journey from writing imperative code to functional code, or maybe you're eager to simply sit down and write functional style code. First of all, I want to emphasize we are not in a competition. So don't feel compelled that you have to write functional style code, especially in one sitting. And it's perfectly okay to evolve the code from writing it into imperative style and modifying it to functional style. That's a good journey to take. And we're not in a competition, like I said. We can take the journey to write the code. And secondly, I'm a big fan of this mantra, make it work, make it better real soon. So I would rather have a working code and then come back to improve it rather than have no code at all and then spend the time saying, I will one day write a perfect code. So for that reason, oftentimes I tell my developers, I really care about writing unit tests on a piece of code which is imperative. And if you write really good unit tests, we can then sit down and refactor the code to functional style. But if we don't have an automated test to tell us the code is working, then if we modify the code, whether to make it functional or not, we have a risk of doing something that's not really the right behavior of the code. And in all honesty, this happens so often. I would take a piece of code that is imperative, I would modify it to functional style, and feel so happy that I was able to modify this into functional style. And then I would run my test and watch it fail right there in front of me. And that's when I would understand that I haven't really figured out what the imperative style was doing. And I thought I understood it, but I didn't really. And I would go back and read the imperative style code, get a deeper and better understanding, come back and modify the code again to functional style, then watch the test to pass. So having that feedback loop is extremely critical. Even though I'm not using a test in this particular exercise here as I'm refactoring, generally speaking, that's something I really encourage and use to just get that feedback loop. But these are relatively small piece of code, so I'm going to just wing it by running the code, and you can see that it's actually producing the output. I want to get exactly the same output when I modify it. Now let's talk about how do we go from imperative style to functional style. Well, in this journey, one thing I realized was if I try to go from imperative to functional style in one shot, I get tangled up, I get confused, I get frustrated, I get angry, and I get really overwhelmed. But then I realized before I go from imperative to functional style, if I make one stop in between and to think about this in a declarative way rather than functional way, that gives me a relief of really thinking through the concepts. So my recommendation is think declaratively and then program functionally. So after all, a functional style code is declarative. So if I force myself to think declaratively, my mind tells me just focus on expressing what the problem is and what are the steps you would take to solve it rather than how you would actually go about solving it, and that what really helps quite a bit. Let's take a stab at this with that kind of thinking in here. If you look over here, we have a for loop, And what are we doing? We are working with a range of values from 1 to 8. So given a range 1 to 8, we want to print if a number is a prime number in that range. Well, if I put those into those words, I'm tempted now to go look for a function that will give me a range, and it turns out there is actually a java.util.stream.intostream contains a function, if you will, which contains the range function we could actually use. So in this case, we can say intostream.range, and the range function, so to say, comes in two flavors. A range 1 to 8 would actually go from a value of 1 through 7. On the other hand, a range closed would actually include the value 8 as well. Well, after all, in this particular example, I have a less than 8, so range is sufficient. I don't need range closed. So I can say intostream.range, and then I can say for each, and I get the value of I that we have in the for loop right there, and then I can simply output right there, and I can say in this particular case, pretty much take that print line function right there, I can bring that over here, and I can say print whether the value is a prime value or not, and we can close that right there. So in this case, we are converting from the traditional for loop into a intostream, and we can simply turn that code into a functional iteration by using the range function. But of course, the real effort here is in the function above, but how do we go about dealing with it? Again, think declaratively. So think, first of all, think declaratively and then code functionally. So essentially, as the question, what are we really doing? Let's put this into words. So given a range of numbers 1 to number minus 1, we can say then no number, we can say in that range, no number in that range divides the given number. So once we express this as a way to determine, at least based on this algorithm here, to determine if a number is a prime number, we can say given a range of numbers, no number in the range divides the given number. So then what we can do here is we can simply take this return number greater than 1, and we don't need this divisibility, but we want a range of numbers. We already know how to do that. So we can say intostream.range from 2, pardon me, not from 1, but from 2. So we can say from 2 to the number, and that will be 1 shy of the number minus 1. And then, of course, we want to say, but no number matches. That's what we are really interested in. So that's basically a function called none match that we can actually use. So this helps us if we become familiar with code. But unfortunately, though, I think you will agree, we cannot just sit there and look for all the code that's possible. So it's a question of just figuring things out in layers. Oh, I want a range. You start investigating in stream, and then you ask the question, as I'm iterating, is there a way to check for condition? And as you look into in-stream, you realize there is a function called any match and all match and none match, and you're like, oh, I could use one of those, and we can arrive at this function. So given an I, we could say number mod I is equal to 0, but we say none matches that particular criteria, and then we are saying that's what we want to return. So when we go back and run the code, we can see that it still works and produces the result, which is the same as the previous result, but we refactored that into a functional style here by just looking at it and expressing the problem in words into declarative nature, and then figuring out what the higher order functions we could use to get the work done. Now, obviously, one problem we may face here is, what about the performance? In the case of a for loop, we were really good at breaking out of the loop when the match occurs. What about this one? Well, the good news is functions like none match and any match and all match are really good at short circuiting. So those functions will not evaluate every single value, and the first instance they can be conclusive, they will bail out. For example, if you call any match, well, if you have 1,000,000 elements, it doesn't matter. Any match will immediately terminate execution the first time it finds one match, that is. In the same case, a none match will bail out the first time it finds that one doesn't actually match. So as a result, if you take an even number, it's going to bail out the minute it gets to 2, for example. If you take an odd number, the first match it sees is going to get out. So only truly a prime number would actually end up evaluating, and everything else would be a fast exit from here. So we wouldn't have any performance concerns. It's going to perform just about the same as the imperative style code we saw a few minutes ago. So what did we do in this refactoring? What did we learn from this? We went from imperative style to declarative style first, and then from declarative style we jumped down to the functional style, and the reason we did that is functional style is declarative. Well, the good news is there's a lot less noise here in the code after refactoring. There's also no garbage variables. If you look over here, we don't have that variable called found. We don't have all that noise of incrementing index variable. We don't have that if condition and all that. So less noise and no garbage variables as well. And then finally, of course, we are using higher order functions to solve the problem. In this particular case, the for each is a higher order function. And so is none match, which is a higher order function as well, because both of those functions take a function as an argument, in this case the lambda expression. So we have built it with a functional style in that particular case. So that gives us an idea how we could make this transition to go from imperative to functional style. So think declaratively and then program functionally along the way. Best time to ask questions is any time along the way. I'm not sure if there's a way for people who are remote to ask a question or not. If they do, I'm assuming Matt will read that for you for me. Awesome, thank you. So don't hesitate to ask a question. Of course, if you're local, you can speak without having to unmute our chat. So feel free to speak anytime. I'll be delighted to hear your questions, your thoughts, anything you want to say. So what we saw in this particular example is a transition from imperative to functional, but by via or a way of declarative style. But that is something I would constantly do, and in all honesty, that's one of the things I always remind myself is, let me think declaratively rather than trying to rush to finding a functional style implementation. And especially this has helped me quite a bit when I've taken more complex problems to solve. And the more complex the problems are, the more important it is that we think about declarative style and then think about functional after that. Let's take on a next example here. And this one here is going to be a problem where we want to take on a little bit more. Let's look at the main function really quickly. In the main function, all I'm doing is I have a local host is set to a variable called search word. Then I'm going through a file which is etc host, but it could be any file you want to read. But I want to be able to count the number of lines with the search word in it. So how do I really find the number of lines with that search word? Well, as you can see here, I have a long count is equal to 0, and a buffered reader is equal to new buffered reader wrapping around a file reader. Then that scary null is a smell, and where we create a line is equal to null. Then while line is equal to buffered reader dot read line is not equal to null, what a scary code, isn't it? And then of course we, if the line contains the word, we increment the count and we keep looping through it until the very end. And then in the finally, we say the word, whatever the word was, occurred and how many times it occurred, and we print it. So in this case, it says the word localhost occurred 3 times, it says. And of course, we have to handle the exception. If the file were not present, we want to know that it was not present, and maybe want to display a message about it, and we want to move on. So the question is, how do we really go about writing this code in functional style? Well, once again, think declaratively before trying to jump onto a functional style. So what are we really trying to do here? Well, we want to take a file, but we want to be able to, in the file, see how many lines contains a word we are looking for. But before we try to do this, let's fall back on a few things we know or we have practiced along the way. And one of them is a stream API in the case of Java. Now, this is true by way of streams in Java, but in general, though, what are we dealing with in functional programming? In functional programming, we have a stream of data that we are really dealing with. And typically, the functions we often use are functions like filter, map, and reduce are the common functions we focus on when it comes to functional programming. So for example, if I'm given a collection of data, numbers, let's say, and if you ask me to find out how many of those numbers in the collection are even numbers, well, we know we can do that easily using a filter function. So then the question really is, in a functional pipeline, we can use functions like filter, map, and reduce. So the only missing part of the puzzle is, how can we go from the content of a file into a functional pipeline? Or how can we go from a content of a file into a stream of data? And as it turns out, that the JDK has been developed to really provide that capability quite extensively, if you will. So when I run the code, you can see it produces that output right there. But let's go ahead and add a java.nio.file.star for a minute. So I'm bringing in here a package NIO file, but then I'm going to say in here a files dot, and I'm going to say lines like so. And the lines function is a beautiful function that is capable of returning a stream of data of a content of a file. So all I have to do here is simply say paths.get, and the path I'm going to give for this is the path I am interested in, which is a variable that is sitting up here. So I'm going to go ahead and simply say output, and let's output the result of that call to the lines function like so. So when I go back and run the code, you can see it provides a stream, reference pipeline, and a head. So essentially, what we are able to get here is a stream of data by calling the lines function. Now that we have a stream of data, the next step here is to simply say filter, and we have a line that comes from the file, and we can say this code right here, which is to check if it contains, we can move it up here and say the line dot contains the search word. So I just moved that part from the imperative style code into here. Well, then the next step is, remember, filter, map, reduce. Well, there's nothing to map here because we are really interested in a line that contains a particular word or not, so there's not a whole lot of mapping. But we want a reduce operation. Well, what am I going to reduce in here? Well, if I really follow a strict a norm of filter, map, and reduce, you might be tempted to say a count is equal to, and you could say 0, and a little silly way of writing it, you can take a line and say, I want to return a 1 because I found a line, and as a result, it's a 1 value, right? And then I can say, here is a reduce, and then I can say total, maybe comma value, and I can return a total plus value. So that's a bit of a roundabout way of doing things, but nevertheless, that actually worked. But that's because I want to think in terms of filter, map, and reduce. But then I realize reduce is a pretty wicked operation. When you think of reduce, you want to think of a reduce as actually a series of transformations you perform to convert a stream into a non-stream. But let's step back for a minute and think of a reduce for a minute. If you think of a reduce, I like to use an example of a floor mat in a gym. So let's say you are going to work out in a gym and you use a floor mat. Maybe you decided to work on a plank and you finish your workout, and as a civilized person using a gym, what do you normally do? Exactly, I can see you are assigning what you would do. You are folding the mat. Well, typically what we do is a mat is on the floor, and you roll the mat into a cylinder, and you stack it up a wall, and then you walk away. Well, rolling the floor mat, folding the floor mat, or drawing into a cylinder, think of that like a reduce operation. So a reduce operation says, given this collection of data, I want to fold it into, or reduce it into, or accumulate it, which is kind of funny because if you look across programming languages, it's as if the authors of the language got to dinner one day and talked to each other and decided they will all use different names, so they will never be consistent. So if you look at C#, the function is actually called as aggregate. If you look at Groovy, they call it collect. If you look at Scala, they call it fold left, for example. And Java uses reduce, and why not? So Ruby says we'll call it inject. Well, so these are all different names, but reduce comes in different flavors. But one of the things we need to really get good at is recognize reduce when it's not being called as reduce. So in this particular case, what I can do is I can get rid of this map, I can get rid of this call to the reduce function, and I can simply say count. And when I say count, you can see the result is still a 3, but wonder what count is. A count is a specialized, if you will, is a specialized reduce function. That's what it really is. So essentially, what you're doing is a filter map reduce. Well, there is no real map in this particular case, nothing to transform. So it's a filter and a reduce is what you just did here. So it's a reduce operation. So when you look at a count, you need to really see it as a reduce operation because that's what it really is. It's a reduce operation. So in this particular case, we filtered the lines. So essentially what's happening in here is that the files.lines is taking the content of a file and it is sending it as a stream of data, in this case stream of strings, and you are receiving that string here essentially as an argument. That's what you're receiving in the line. And you're taking that string, of course it helps to spell it properly, and you're taking that string and then you're asking, does the string contain the word I am looking for? And if it does contain that word you're looking for, then eventually you're saying, I want to like count the number of lines and return the result from it. Now, of course, the lines function will blow up with an exception if the file were not present. So as a result, you still need to wrap it into a try and catch block. But on the other hand, once a stream gets flowing, the filter and the count takes over, and you're in the functional pipeline to work at this particular point. So we went from imperative to functional, but of course, again, we reasoned through it. No explicit mutability in this particular code. So as a result, if you think about the code we had a few minutes ago, we were performing a while loop and we were incrementing the count. And if somebody comes to you and says, parallelize that code, the best response is to laugh, because you only have a couple of options here, to laugh or to cry. Because an imperative style code is incredibly difficult to parallelize. Whereas here, you can parallelize this code if you choose to. What if this file is a very large file and maybe you want to make it parallel? Maybe you can say parallel, and you can parallelize this particular code potentially maybe, and you could do that as well. It's incredibly easy to parallelize that code where that may be necessary. And the reason for that is we don't have explicit mutability. And when we don't have explicit mutability, the code is naturally easier to parallelize. It's also less error prone, and that becomes a lot easier. But the approach we took in this particular case is that we first identified that if we were to use a functional pipeline, we want to rely upon a filter, map, and reduce. And then we realized, oh, we could convert the file into a stream and then hook it up to a filter and reduce. And that's basically the operation we performed in here. So that was a good transition into the Stream API. But taking that a little bit further down, now let's take a look at a particular code which is going to be really sad in terms of the complexity that's going to come into the code. So let's take a look at an example of a code here. So let's look at the main function. The main function pretty much has a hash map, a map, where the map contains a bunch of names and score values in the map. You can see there's a Jack who has 12 points, Jill has 15 points, Tom has 11, Darla 15, Nick has 15, and Nancy has 11. So what we know is the names are different. However, the scores are not unique. It's possible that two people may have the same score. So what I want to do here is I want to group the people based on the score. So I may want to say for 11, I have Tom and Nancy. For 15, I have Jill, Darla, and Nick. For 12, I only have Jack. So when I run the code, you can see that in the output. 11 has Tom and Nancy, 12 has Jack, 15 has Darla, Nick, and Jill, and that's a result I want. But how do I really write this code? Well, in the imperative style, this progressively becomes really worse. Imperative style is filled with accidental complexity. So if you look at the code basically we create a map where the map key is an integer and the list of strings is the value within the map. Then we say take a name from the key set and first of all go to the map and get a given map and get the score. Then create an empty array list. Check if the score is present in the result map. If it is present, go ahead and get that particular list from the map, replacing this empty array list. A poor garbage that got created is thrown away right there. And if it is not there, simply use the empty list. Go ahead and add the name to that list, whether it's empty or not, and then put it back into the collection, which is a redundant operation if it is already in the collection, but we had to do it because if there was no value in the collection in the beginning, we had to add it. If we don't want to be redundant here, we got to perform a check one more time, and that's a question of do you want to perform a check one more time or just simply add it. But in any case, that code is not something you would be proud of. You don't go to guest in your house and say, let me show you a code I recently wrote, right? That won't be one of those things, nothing to be proud about. If at all, this is something you will hide from anybody. And of course, this is a code you would not want to write too often, and you're so eager to hire that intern so you can give the code to the intern and say, you write the code, and while they happily end up writing that code, you're like, my goodness, I don't have to write that code, right? Well, I would say, if you have to write a lot of that code, it probably borders some inhumane and maybe cruel and unusual punishment that we take on ourselves. So what can we do to eliminate this kind of code? Well, the first thing is, again, let's think declaratively before we go functionally. So how would you want to really program in a declarative style? Let's step back for a minute and ask the question, what are we really trying to do? It really becomes easier if we are able to imagine a little bit. So imagine for a minute that you have these values that are being given to you one at a time. So you are given a key value pair, an entry. So you have Jack and 12, Jill and 15, Tom and 11, and so on. And imagine in front of you, you have buckets. And imagine those buckets have a label on them. You have a bucket with a label 12, you have a bucket with a label 15, you have a bucket with a label 11, and so on. Now imagine yourself, you stretch your hand and you're given Jack with 12, and all you're going to do is take Jack and drop into the bucket with label 12. You're given Jill with 15, you take the word Jill, drop into the bucket 15. You're given Tom with 11. You take the word Tom, drop into the bucket with the label 11. So essentially, you want to go into a bucket and you want to really map into a bucket. That's what you want to really do. Well, once you realize all you're looking for is a bucket operation, next the question is there a function in the JDK that can give me that kind of a bucket operation? So let's go back to this code right here, and let's go ahead and say we want to take this list, the scores given to us. So the scores given to us, of course, are going to contain the names that are flowing in, because the names are the key that we have, and it becomes easier to work with this key. If you give me a key, I can get the value. But if you give me a value, it's hard to get the key. So I still want to work with the key. So what I'm going to do here is to say scores.keySet, and then I'm going to call upon a stream on it. So this says I want to get a key set and get a stream on the key set. And once I get a stream on the key set, what do I want to do? I want to call a collect function. Now, what is a collect? Keep in mind, collect is a specialized reduce operation. Because you're going from a stream to a non-stream, it's a reduce operation. I'm going to bring in the collectors static methods, but then I'm going to say over here grouping by. So I want to group by. What does the word grouping by simply means? I would like to call it as toss it into a bucket. That's what you're really saying. Grouping by simply says what is given to you, toss it into a bucket. But what bucket do I want to toss that into? This is basically saying, given a name, toss it into a bucket with score for the name. That is basically what you're trying to do, is you want to toss it into a bucket with label, which is a score for that particular name. So I'm going to simply say name.get, pardon me, scores.get. So scores.get for the given name, and I'm going to get it. So what did that do? That simply provides for us the bucket we are interested in, and I can return that, and I can get rid of all this code now and simply return the result we get back over there. So as you can see now, 11 is Tom and Nancy, 12 is Jack, 15 is Darla, Nick, and Jill. So what did we do here? We take the keys like we did before, and for every key, we are saying get the score and toss the key into a bucket with the label, which is the label of the score. Now, that code worked, but a quick little refactoring, if you will, it turns out that this one here is really a method reference you can use, because all it was doing was a pass-through lambda. So as a result, you can replace that with a method reference like so. So you don't have to really write a lambda right there. You can simply say scores : get, and you can simply use a collect function. So you can see how that monstrous code with all that creating an empty list and checking for values, all of that simply went away. But it went away because we realized we can apply a transformation where we can simply transform this into a series of buckets where the buckets are a label. So thinking in terms of what we are doing is we are taking the objects given and tossing them into different buckets, which is what grouping really is. And then we find out that we can actually use a grouping function, which is literally creating these buckets of data and tossing them, and then collects them into a map and returns it to us. And that's basically what we did in here. So, but of course I have to admit, the more we dig into the collectors API, the more complex it actually becomes. It is something that I would say is probably going to take a little bit of practice. And there are so many functions in the collectors API, but what's even more interesting is that a lot of these functions actually are really very recursive in nature. What I mean by recursive is that you can create a collector using a function, but the collector function itself can be built using other collector functions. And so you can create a very complex set of collectors, and something that I would say takes quite a bit of effort to get it really working. So the code can be extremely concise, but it takes quite a bit of effort to actually write it as well. So do take the time to really practice it and get better at it. Don't feel frustrated if it takes a few iterations to get really comfortable with it. So that's basically what we saw here in terms of using the grouping. So we took a fairly verbose code and we made it relatively concise. It's very expressive, as you can see, compared to the code which we had to write where we were trying to really initialize the empty array and looking for the value, adding the value. All that complexity just went away. And of course, it is very declarative, and we are using some specialized functions in this particular case as well to get the work done. Now, the next problem I want to talk about actually is something that I have to admit is not my problem, but a problem that was actually sent to me. One day I got an email from a person who said, hey, I saw you talk about functional programming. I saw you use examples of filter and map. I get it. But here is a problem, and I have no clue how to solve it using functional style. Can you take a look at it and let me know? And so this was literally the problem this person sent me, with the Pythagorean triples, and you will see the code is quite a tangled up mess that we're going to see right in here. So if you look at the code itself, you will notice that the code is really trying to use an algorithm to find. So what is the objective here? Well, first of all, the objective here is to find a set of A, B, and C so that the A, B, and C satisfy the equation A square plus B square equal to C square. So the goal is to find numbers that satisfy this. Now, clearly, that's an infinite series of numbers. We can't just sit there and keep finding those numbers, or we'll get old and die doing so, right? So you may want to set a limit as to how many numbers you want. But notice that in this case, what I'm doing is I am calling the compute triples with a value of 10 to say that I only want 10 values given to me. But then I say for each, just simply print them out. Okay, great. But how is compute triple do the work? Well, this is using, there are several ways to do this. One is to use what's called the Euclid's algorithm. And the Euclid's algorithm says you can find a triple that satisfies the formula A square plus B square equal to C square by doing so, given a M and a N, where an M and N are, have a certain rule. M is greater than or equal to 1, and N has to be a value 1 through M minus 1. So that's just a restriction. But then, if for a given value M and N, you can say A is that, B is that, and C is that. So if you give me an M and N that satisfies what we talked about, which is M is greater than 1 and N is less than M, then we can use M and N and to determine a combination of A, B, and C which satisfy the equation that we talked about. Well, so get triple is easy to use, but the question is, how do we navigate and get all these values? Well, this is the code the person sent me, and here's what the code was doing. We have a triples, which is really a empty collection to begin with. We say count is equal to 1. For M, which is greater than 1, so starts with a 2, and it's an infinite loop, and M is M plus 1. Then we have an N, where N is starting with 1, and it's 1 less than the current value of M, and we increment N. Then we say triples that we created here, the empty collection, dot add, get me a triple for this combination of m and n. Increment the count. If the count is greater than the number of values I wanted, break. We come out of the inner loop, but to add insult to injury, we have to check again. And then if count is greater than number of values, break again and get out of the loop. And eventually, pardon me, we return the triples right here. We wanted only 10 values. So you can see a 3, 4, 5 in the top, 9, 40, 41 in the bottom, and values in between. Now when you look at this code doesn't feel that exciting. It works, but it looks verbose. It looks really sad that we had to perform this comparison not once but twice in here. So the question is, this is definitely a very good example of a complex imperative style code. How do we really make this code into functional style? So the person who emailed me said, I know map, I know filter, I know I can use a functional pipeline, but how in the world can I solve this particular problem? So where do we go? What do we identify here? What I want you to look at here is, it's not the code you look at, it's what you see that matters, as they say, right? So you want to look at a couple of different things going on here. The first thing you are looking at here is, you have a m that goes from 2 to 3, 4, 5, 6, and so on. Ta-da, we have a series on our hand. Well, that's an m series. Great. Then you have an n series. The n series goes from 1, 2, 3 all the way to 1 shy of m. So if m is 2, n is 1. If m is 3, n is 1 and 2. If m is 4, you have 1, 2, 3. But you can see there are two series here. There is an outer series and there is an inner series. But then notice what's going on here. If you only focus on the inner series, what's going on in the inner series? In the inner series, you have a collection of data that you are creating. Imagine for a minute that we don't have two series. Imagine we only have one series only. If you only have one series, what operation would this look like then? If all you're doing is, for one series of value, you're getting one value computed for every value, and you want to produce a result out of it, right? So think about it this way. So we have one series, right? A series. So 1, 2, 3, all the way to, let's say, some k. And then, oops, sorry. So let's try this again. So we have one series, let's say 1, 2, 3, all the way, right, up to a value of k. And for each value in the series, right, compute f of some x. So, and then in the end, create a list of values of f of xi. So question in this case is, what functions would we use to solve this particular problem? Any thoughts? What would we use? I'll give you a clue. Two functions, right? Sorry? Yeah, range, fair enough. For the range for 1 to k, so you would say range, maybe range closed, right, from 1 to k maybe. Then there's two more functions you would use. What's the next one? Because for every given value, you want a transformation of the value, right? A map, absolutely. You would use a map and pass the function to it. And then what's the last value we would use? Bingo, a reduce or a collect in the case of Java, right? So because collect is a reduce, and you're absolutely correct. But the catch is this: you can use a map, but what you have to in this particular case is not a series, but you have an outer series, right? So we have an outer series. So what that ends up being now is you have an outer series and you get into an inner series and you do a map, but then you're like, wait, it's a map of a map. And it kind of throws you in a spin, right? It's like, what's going on here? So let's think about this a little bit differently. Sorry, setting for me? You can try to collect them into it, but before we go that route, let's think about this a little bit further. If you look at one series, what are we looking at? So for one series, for each element, we get a transformed element. So in other words, it is a one-to-one mapping, right? It's a one-to-one mapping. Now, if we have an outer series and an inner series, right, then what's happening? For each outer element, we get a series of values from the inner series. So in other words, what is this? This is it is a one-to-many mapping. So it's not a one-to-one mapping, it's a one-to-many mapping. So when I read this email from the person, the immediate thought in my mind was, aha, we are dealing not with the one-to-one mapping, we are dealing with the one-to-many mapping. Now, leave the thought aside for a minute. We'll come back to this in a few minutes and think about it. So now that we thought about one-to-one versus one-to-many mapping, leave the thought aside. We'll come back to that in a minute. Let's switch gears here, if you don't mind, for just a minute. And I'm going to use Kotlin here, not for any other reason than the fact that Java doesn't have this function. I can use Ruby, I can use Kotlin, but because we are talking about Java here, why not just simply use Kotlin? So let's go ahead and take a look at an example here of Kotlin code and play with it. So let's take a little example to play with. I'm going to blow away everything in this directory right now. So let's edit over here a sample.kts. So let's say a val numbers is equal to list of 1, 2, 3. Let's take a really small example. So I'm going to say print line, well actually let's say result1 equal to numbers, let's say dot map, and given an element, I want to return an element times 2. So in this case, if I want to print out result1, what is the result going to be? For each of the values that you can see, I got a 2, 4, and a 6. But take a look at this function for a minute. It's a one-to-one mapping, right? Or one-to-one transformation. That's what we have. So that was pretty simple. But on the other hand, if I were to take, let's say, in this case, a value 2, a result 2, like so. But this time, I'm going to go in here and say, this is going to be a list of I minus 1 comma I plus 1. So I'm going to return a value before and a value after. So if you give me 1, 0 and 2. If you give me 2, 1 and 3. If you give me 3, 2 and 4. But when I run the code, what do I see as an output? Well, what I see as an output is a list of a list, isn't it? But the reason why it's a list of lists is it's a one-to-many transformation. That's what we have in here. Now, obvious question is, do you really want a list of lists, or do you want a list alone, right? For example, right, here's the way to think about it. We got, amazing developers here, and I can say for every single person in the room, I want to know your age. Okay, maybe that's not an appropriate question to ask, but hey, we're among friends, right? And nobody knows what you're saying. You can give any age you want. So what does that mean? Well, every person, I'm assuming, has exactly one age. And so that's a one-to-one mapping. So if you give me a list of people, I get a list of age. Hey, that's great. But on the other hand, I am going to say, I want every person in here, I want your email addresses. Well, we are tech people. What are the chances we have one email address? We're going to have several of them. And you say, which one do you want? I want all of them. If I'm going to spam, why not spam in every one of them? But then you say, cool, here you go. But what in the world is this? You gave me a list of people, but the output is a list of email. I'm like, I don't want a list of email. I just want one list of email. Well, that one list of email contains emails of everybody thrown together, and that's perfectly fine. So in other words, what do I want to do? I want to take this result 2, if you will, and I can say over here, val result3 equal to result2 dot flatten. And then of course I can go back and print out right here in this case, and I can say result3, and I can print it. Notice the result3 is a flattened list. So the 0, 2, 1, 3, and 2, 4. But wait a minute though. That's great so far, but I'm going to be a little lazy. When it's a one-to-many operation rather than a one-to-one operation, why not get rid of all of this and simply say dot flatten and flatten it right there, right? So map it and then flatten it. Well, that's awesome so far, but why not merge that into one function? Now, be extremely honest here. If we're going to merge that function, what would you call the merged function as? You perform the map, and then you flatten it. So logically, what would you call it? Map flatten, isn't it? Now, here is a little puzzle for you. And be brave. Try to say this. Go ahead and say map flatten. Go ahead and say it loud. And say it about 3 times. What did you notice? Do you feel that sharp pain right there in the junction of your jaw? If you have kids at home, those who are remote, try this. Invite your kids and ask them to say map flatten a few times. And they're going to say, Mom or Dad, that hurts right here. Map flatten, right? That's an awkward movement of jaw. The people who created this API are geniuses. They not only cared about programming, they have humanity. And they realized if they called it map flatten, they're going to have broken jaw for people eventually. And they're going to have pain in the mouth like I'm having right now because I just had a surgery a week ago. And it's not fun to have a jaw which is painful. So they said, all right, let's save the world. It is honestly map flatten, but we're going to call it flatMap. Why did they call it flatMap? Now try saying that, flatMap. Notice how it rolls off the tongue. Your jaws don't hurt anymore. Now you know the rest of the story. So why do they call it flatMap? It actually maps it and flattens it, but it's called a flatMap because map flatten is really awkward to say. Well, now that we know where are we going with this? Where we're going with this is if you have a one-to-one transformation, use map. If you have a one-to-many transformation, use flatMap. So what does a flatMap do? It maps each of the value into another collection. And then it flattens it for you, and that's why you would use a flat map. That is really recognizing that you are dealing with the one-to-many function. Oops, if I know how to type this. You're dealing with a one-to-many function after all. So now, let's go back to this code right here. Notice That's the result we are expecting after we refactor the code. 3, 4, 5 in the top, 9, 40, 41 in the bottom. But what we're going to do here, though, is we're going to say, hey, we came in here with the number of values. We want to compute the triple. And like you pointed out correctly, we want to work with the stream dot into stream. That's what we're going to start with. So we will first of all say over here into stream dot range. And what are we going to start with? Oh, darn it. It turns out this is actually an infinite stream problem, right? Because m is never ending. So I'm going to say return stream.iterate, start with the value 2. Why am I starting with the value 2? Because m starts with the value 2. So starts with the value 2, and then comma, m is going to be m plus 1. So we started the outer iteration. Then we say dot map. And what do we want to do? Given a m, we are going to say into stream dot range from what? From 1 to m. Because notice it's 1 to m, right? Or 1 less than m. So range instead of range closed. But then what am I going to do? I'm going to say map. And given the m and the n value, I want to call get triple. And notice what we are doing with the get triple with the m and n. So m comma n, like so. So, but then what's happening here? Well, this is giving me multiple values right there, but it's going to give me a map as a into stream. So it's a map to obj. So it becomes a stream at that point. Now that I get a stream, what am I going to do here? It's a flat map I'm going to use. Then I say limit to number of values, collect it to a list in the end, and return it. And so I'm going to go ahead and bring in collectors for the toList function. So what we did here is we said start iterating from the value 2 for every m value. Go get me a collection of the triple for m and n 1 to m minus 1. Flatten it as you transform it. And once you flatten it, only get me that many values. No need to compare it twice after all. Just one limit is enough, as you can see right there. And then put that into a list and return it. So now if I go back and run the code, all that code that was extra, right, goes away, and the result is the same. But what was the trick here to find the solution? It's recognizing the fact that we are actually dealing with not a one-to-one transformation, but a one-to-many transformation. The minute we recognize that's a one-to-many transformation, our mind is like, oh, that's a flat map operation, not a map operation. That was the giveaway in this refactoring that you want to look into. So the last refactoring I want to do here is going to be somewhat along the lines, but we used functional composition, we used lazy evaluation, but the real trick here is recognizing that one-to-many. In the next one, we are going to take a small problem here, which is going to provide a lazy evaluation. So if you look over here, the compute sum of square root of primes, that's the name of the function, right? So compute sum of square root of primes. 101 is the starting point. I want 51 of them. Run the code, it produces a result 770.34, blah, blah, blah. But if you look at the code, there's a prime we are determining, but then the compute sum of square root of prime says, I'll start with an index of start. The computed count is 0, sum is 0, while computed count is less than count. If the number is prime, find the square root, put it, add to the sum, increment it, increment the index, return the sum. That's a complex piece of code. We got to make sure we are doing the increment in the proper place, not inside or outside the condition, and so on. that looks pretty complex, but what are we really trying to do? As it turns out, this is saying you keep computing until you run out of the values, how many ever we want to compute, right? So while. It's not a for loop because we don't know which number is a prime number. So you keep counting until you are counted as many. When you look at a problem like this is a prime example of what is called an infinite sequence. Well, infinite sequences are possible in Java today because we can do lazy evaluations thanks to the ability to do lambda expressions. So as a result, we can greatly benefit from having this lazy evaluation on our hand. So how do I make use of lazy evaluation in here? So basically in this case, we can take this one here and we can say a stream we are bringing in, but in this case what am I going to do? I'm going to take the compute and say return stream.iterate. I'm going to start with the number start, and I'm going to say given an element plus 1. Then we say a filter, and I'm going to simply ask for only prime numbers, so call isPrime right there. So we filter out only prime numbers from this collection. Then we perform a map, and we say math, and this is going to be a square root operation, and in this case of course I'm going to say map to double. But then we do a limit, and we ask for count number of values and perform a sum operation. Now the beauty of this is we can get rid of all the other code we had to write here, and all that goes away, that complexity. So when we run the code, we get exactly the same result, well, almost as we did before. But what did we do in here? We start with the infinite series, the value plus 1, value plus 2, and so on, keep going. Get me all the numbers starting with start. Get me all the prime numbers that start with start. Get me the square root of prime numbers that start with start. But get me only the count number of those and total it. In this particular problem, you can move the limit up here if you really wanted to. But of course, you cannot move it up here. If you move it up there, it's going to take n values and then find primes, which is not what we wanted. But if you move it up here, that's perfectly fine because you wanted that many prime. You can also move it here if you really wanted to. So there's a bit of a leeway in where you can put it, but you cannot just keep moving it. So you got to logically ask, do you want n numbers and then prime after them, or do you want n prime numbers? Logically speaking, I would put it right here because it corresponds closer to the problem given to say you want to take n prime numbers and find the square root and find the sum, and that becomes a lot easier to work with. So that becomes refactoring using the infinite series. So one of the really cool things about this here is that the infinite series allows us to express a problem in a very elegant way, but we're able to use infinite series because lambdas can be evaluated lazily. And this is a departure from what we did in Java before, where Java typically did eager evaluations only. But now Java can do a lazy evaluation as well. How so? Where's a way to think about it, if you will? Suppose you have a function, let's say, you have a public, let's say, static void, let's say, or static int compute, and I'll call this as int some number n, and I want to simply, let's keep it really simple, return n times 1, which is kind of silly, but I want to really say output, let's say, called. So in this example, as you can see, if I were to go back to this code and say something along the lines of this, let's say we have a public, let's say, static void print 1, which takes a number n, and I'm going to simply call over here output the value n. Now if you look at this here, I can say a print 1, and in this case I could say compute and send a 7 to it like so. Now in fact, to add insult to injury, in this function I can say if math.random is greater than 0.5, I'm going to output right there and I'm going to say output, let's say skip. Otherwise, I'm going to output the value and be done with it. But the interesting part about this function is, when I call this code, compute is called and skip is called. What does that tell us? That call to compute was a total waste, isn't it? If I run this again, the called and 7. But if I run it again, you can see called and skip. So the call to called is a total waste. Well, but the reason why it is a total waste here is, this is what is called an applicative order. In other words, Java will eagerly evaluate. Java doesn't care whether the value is used or not. But what you can do, though, is a little bit of a twist, if you will. Let's take this code right here, but let's rewrite it as a print2. The print2 does a skip like the other one did, and it's going to print the value. But I'm going to change this value here into a dot function dot, and I'm going to go back to print2, and I'm going to say this is a supplier of integer, and we will call this as that value n. But I come in here and say n.get. Well, now what's going to happen? If I go back to this code, if I say print2 right here, right? So print2, but I'm going to turn this into a supplier. So I put a little arrow right there. So when I run the code, notice it said skip. It didn't call the compute. If I run it again this time, notice it said called and 7. So this is a deferred evaluation. In other words, by passing a lambda to a function, you can say you don't need to run it right now. You can postpone running it. Now, look at this again. That's a lambda you're passing to the iterate function. The iterate function says, I will not run this lambda now. I will run it on a delay, and I will do it on demand. Only when you want more values will I produce more values. Here's a way to think about it. Imagine it's a busy day, and you want to go to a public office, like Department of Motor Vehicles. And you go there, and there's a crowd, and what do they say when you walk in? They say, pull a ticket. And you walk to a little ticket machine, and you yank a ticket out of it, and you take a deep breath and say, damn it, that's a 275, I've got a long wait. Well, the next person comes in, pulls a ticket, that's the next one. The next person pulls a ticket, that's the next one. Well, every time somebody pulls one, that number is incremented. Or think of this like your primary key in a database. Well, every time a data is inserted, a primary key is incremented. Those are examples of infinite series. The increment doesn't happen until on demand. And that's exactly what this code is doing. It says, I'm going to keep incrementing the value, but only when you demand to get more. And the minute you say, I'm done, I'm not going to evaluate it. So it gives a nice balance between creating an infinite sequence, but the sequence is not all created in the beginning. It's created on demand. Very, very powerful operation. But you know why that works as well? Because lambdas are evaluated on a need basis, and they're not evaluated eagerly. So this gives a nice opportunity for us to postpone evaluation in our code, and that's basically what we are leveraging here. And it's concise, and it uses lazy evaluation, and we managed to bring in infinite series into this as well, and that's basically what we are doing. So that's the last exercise I have. I'll be delighted to hear your thoughts, answer any questions you may have, just about anything. If you're remote, you can post your questions as well. I'll be delighted to hear your thoughts. If you're local, obviously, you can just immediately speak whichever is convenient for you. Please do. Please.
When you're doing a loop to determine if the number is prime, you don't need the full loop. You just need the couple of loops.
So you don't need the outer loop, you're saying?
No, you just need to not from 2 to number, just from 2 to number divided by.
Oh, yeah, yeah. So, yeah, absolutely, you can optimize the heck out of it, but that's not the point, though. But in a way, I would even argue it's a premature optimization, right? So if you really...
It's not, because there is no any dividers
Yeah,
past that point.
I hear you. I know exactly what you're talking about. But the point is, you're making me think for no gain. It's a premature optimization, right? And that's when we become clever in code. And what did we achieve? Maybe a microsecond performance. So I will always ask the question, why do you want to do it? If you have a really good reason, go for it. If you have no reason, but you want to just fiddle with the code to optimize it, I would say premature optimization.
Every time I'm looking for prime numbers, I just do it this way.
Yeah, and I wouldn't do it. That's what I'm saying. I wouldn't do optimizations like that at all until I see a real benefit for doing it. Other thoughts, other questions?
So what's the benefit of using lazy evaluation? What
So-
it brings us?
Yeah, so what is the benefit of using lazy evaluation? The very, very first benefit is performance. So if I don't have lazy evaluation, let's step back for a second and answer this question a little bit. So here's a really nice way to think about it, right? So let's say for a minute you say numbers is equal to, really simple example, right? Numbers is equal to list of 1, 2, 3, let's say 4, 5, and 6. This is a Kotlin example. And let's say for a minute I want to say that I'm going to create a function. So let's say in this case we'll call it as a double it. And the double it function says give me an integer. And all I'm going to do here is simply say I want to return back an integer. Take a very simple example here. So return n times 2. So but we'll also output, let's go ahead and say double it, right? Double it called for, and I'm going to say the value of n. So let's take a very simple situation. But the problem I'm going to work here is numbers dot, let's say, and I'm going to say in this case dot filter. And I'm going to say given an element, I'm going to say the element that you're providing for me is going to be, let's say in this particular case, mod 2 is equal to 0. And then once I do this, I'll do a map operation. Then I'm going to say, given this particular element, I want to double it and pass the element to it. But I'm going to simply say the first value is all I care about in this particular example, let's say, right? Just the first value, give the first value to me. But notice what happened here in this particular example. The result is a 4, right? Well, the result is a 4 because this is not an even, that is even, and when we get an even, we're going to get the value out of it, and we're going to provide it. But when you perform the map operation, what are we performing the map operation for? We did it for 2, 4, and 6, which is kind of sad, isn't it? Because if I go back in here, and if I say 7, 8, 9, and 10, what's going to happen? It's going to perform all the way up to 10 and throw all that value, give the result. If you and I were to write a for loop, we would never do this. We would put a break statement in there, right? So now you're saying, gosh, I should really be optimal. I shouldn't be doing that extra computation. And as an argument, some languages may say, what's a big deal? If you're dealing with a small collection, maybe it doesn't matter. But what if a collection is really large? And especially if it's an infinite unbounded collection. Well, you can say as sequence right there. Now, Kotlin gives you that flavor to go one way or the other. So notice now the difference, right? So you're saying, let's get lazy. So if you don't have that line, in the case of Kotlin, you are being eager in evaluation. And it did all the computations. But the minute you put that in there, it was lazy. So you are really optimizing and not evaluating. So on one hand, well, first of all, in Java, streams are always lazy, right? In the case of Kotlin, you have a switch you can turn on and turn off, so to say. So on one hand, I want laziness for efficiency. But on the other hand, because I can be lazy, it opens the door to really create infinite sequences. If I don't have this capability, creating infinite sequences is much harder. And so we can leverage. So laziness gives us efficiency, but laziness also gives us the ability to do infinite sequences too. Yeah. Good question. Thanks. Please.
Yeah. So you said that for functional programming, so it's a declarative and lazy evaluation both.
Declarative plus higher order functions, plus composition and lazy evaluation. Yes.
So for other programming languages that does not support laziness, like JavaScript.
Yeah.
So is it possible to perform functional programming there?
By using third-party libraries, or you have to devise it by yourself. And that's and also, in all fairness, though, I don't want to go overboard with performance. There are times when it's not a big deal. If the collection is really small, you're not going to lose anything by going that extra mile, right? So you had a comment or a observation? Okay, so essentially, if there is a need for it, you want to rely on it, right? Ruby doesn't care. It only gives you the, so I try to distinguish, this is a term I try to use just for my own clarity. I use the word functional style is where you use functional composition, where you have that pipeline. Then I say functional programming is where we do functional composition plus the use of lazy evaluation. So that little extra mile. So in languages like Ruby and JavaScript, you can do functional style. And that has benefit because you can make the code elegant, you can remove the accidental complexity, the code is expressive, and if the data is relatively small, no big deal. But even in JavaScript, for example, if you're using RxJS, a reactive stream library, that has laziness built into it. So the language doesn't provide laziness in its filter and map, but that's a collection. The way it's implemented, they didn't care to provide that. Similarly, Ruby doesn't provide laziness in their collection, but other third-party libraries could do, other data structures could do, other functions could do. So it's not that the language itself doesn't, it is that the implementation of those collections don't. But in all fairness, there is this three camps here, right? Those that are not lazy, period. Then those that are lazy, like C# and Java, the collections are always lazy. You don't have a control over it. And then you look at Scala and Kotlin, they give you a switch. And they say, well, if you don't care for that extra performance, because you're dealing with a relatively small problem, and in all fairness, debugging is easier, right, when it's eager evaluation. So then you can write the code with the eager evaluation, be done with it, and if performance is a concern, you can flip that switch at that time, and it can invoke laziness. And get the best of both worlds, right? You can go back and forth based on what you want to do. So that's kind of the different camps, if you will. And there's no right and wrong here. It's a question of what the preferences are for different use cases that they are aiming towards. But from a programmer point of view, that awareness is still important. Because if I'm not aware of it, then I don't have an understanding of the space-time complexity. And having that understanding of the space-time complexity is really important, right? It's having the knowledge and the wisdom, right? You're like, I know what it's doing, but now I can exercise what I want to exercise, but having that it's a semantics, right? So it's not the syntax, unfortunately, because when you look at the code, it doesn't tell you I'm lazy. It's a semantics that's where the laziness is buried into, and you need to be aware of that. Thank you.
Just one more thing for the, thank you, Venkat.
Thank you, appreciate it, thank you.
So thank you, Venkat, and I already saw some claps in the online audience. So if you are on the online audience tonight, go ahead and email us. I put the link in the comments, denveropensource@gmail.com, if you're interested in getting one of the two door prizes, either Agile Learner or JetBrains product. And so next month we've got Craig Walls coming up, and hope to see you then. Thank you. And you guys can let me know now if you're interested in the door prize.